In this lesson, we're going to take a more formal look at limits and how they can be used in calculus and some of their applications. So this whole next unit is about analyzing functions. And we can analyze functions by looking at different points along the graph, but sometimes we want to know, well, what happens down the road in the future? Or what happens as we get close to a point? What happens if that point doesn't exist? There's a hole, there's an asymptote. That's really the idea of limits. The limits are the study of what happens as you approach a point on the graph. Okay, so a little bit of notation to start. So we're going to use limit notation, which means x arrow a, which is read as the limit of your function is fx, as x approaches a. Okay, and what that really means is we can figure out what's happening as we get closer and closer to a without ever knowing the point a itself. Because in some cases, point a may not even exist. Okay, so our limit calculates the function value as you get close. As I was saying a second ago, not all limits exist. So if a limit doesn't exist, we can figure that out by using left and right hand ideas. So the left hand limit is what happens as you approach from below a point. So let's say I had a graph and I have something going on. As I approach from the left, maybe I recognize that something's happening here. As I approach from the right, maybe something else is happening there. And the way we use our notation is left-hand limits say as I approach a from the negative side. Now it's not actually a negative number necessarily, but from the negative direction, so a negative. The right-hand limit, x approaches a from the positive side, so a plus. Again, it doesn't necessarily have to be a positive value, it's just the idea we're approaching from the right-hand side. For a limit to exist, to actually be able to calculate one, the left and right hand limits have to be equal to one another. If they're not, then that value doesn't exist, which actually tells us something about the function. If the limit doesn't exist, that point doesn't exist. There's something weird going on there. It might be a hole, it might be an asymptote. There's something discontinuous about that graph. If a limit does exist, in other words, if your left-hand limit equals your right-hand limit, then usually the function's continuous, but not necessarily. And we'll come across some situations where we see that. So let's look at the first example, show you how this works. So we're going to use the left and right-hand limits to calculate what happens as we approach 1. Okay, so we're going to do the left-hand side first. So our limit from the left-hand side, x approach 1 negative for fx. So what happens as we get closer and closer to 1 from the left-hand side? So let's pick a value on the left-hand side. I don't know, what's left of 1? Let's start at 0. If I put 0 into my function, I get 0 squared plus 1, or I get 1. And we're going to get closer to 1, but still on the left-hand side. Let's try 0.5. So we'll get 0.5 squared plus 1, and that comes out to 1.25. Let's get closer still. So let's try what happens as we get to 0.75. So 0.75 squared plus 1 comes out to 1.5625. So notice our function value is getting bigger and bigger. Not a whole lot bigger, but bigger than it was before. Let's get really close to 1. 0.99. If we square and add 1, we end up with not 1.9801. So it seems to me, as I get closer and closer to 1 from the left-hand side, my function value is getting closer and closer to 2. And we're going to say approximately. Okay, that's what the little dot above the equal sign means, approximately. Now let's see what happens as we approach 1 from the right-hand side. So 1 plus. Okay, so let's pick a number definitely to the right of 1. So let's try f at 2. So again, we're just using that equation. 2 squared plus 1 gives us 5. Okay, let's get closer to 1. So let's try 1.5 this time. So 1.5 squared plus 1. Same old equation. Okay, I'm not going to stop showing the equation. Okay, our number seems to be going down. Get closer to 1. Let's try 1.1. We end up with 2.21. So our numbers are dropping and getting closer and closer to a certain value. Let's try a really small number here, 1.001, just to the right of 1. We end up with 2.002. what do we notice as we approach from the right-hand side? Well, again, our numbers are coming down, and they seem to be getting closer and closer to 2. So because our limit from the left and our limit from the right appear to approach the same value, we can say with some certainty that the limit as we approach 2 for this, sorry, not 2, as we approach 1 for this function, f of x, has a value of 2. In other words, we think there's a point that exists in the graph at approximately 1, 2. That's how a limit works. What happens as we approach a value? Okay, let's try some more. Graphs are helpful tools. They allow us to talk about continuity and discontinuity, and we're going to do this with limits, a more formal idea. So use left and right hand limits to explain if the functions are continuous or not. Now I can look at this graph and say to myself, well, it's obviously continuous. I can draw every point on it without lifting my pencil. How do I use limits to explain that? Well, let's pick a limit for this function. And as x approaches, and to be honest, it could be any number, right? Anything, any. From the left-hand side, I get a number. So I'm going to actually pick one just for random sake. And let's say, what happens as x approaches 0? Well, if I approach it from the left, let's call this point, I don't know, 0 and 3. It comes out to 3, right, my function? As I approach 0 from the right-hand side, as I go this way, it also approaches 3. What does that tell me about the point 0? Well, since my values are the same, from the left and the right, they both come out to 3, I can say that I think there's a point in this graph that exists at 0, 3. And I picked the number 0 at random, but it could have been true for any point, so this graph is continuous. And I could have picked any x I wanted. I didn't have any values in this graph, but I could say I could pick that x value, that x value, that x value, that x value, that x value. No matter what I do from left and right, my function value will approach the same thing. So my limit's going to exist for every point on this. If we look at the second one, and I think about, well, it looks discontinuous, how can I use limits to prove that? So let's look at the number 0. If I approach it from the left, what happens to my function value? Well, it seems to be going up and up and up and up and up. In fact, it's approaching infinity. Okay, the closer I get to 0, the higher that line goes. If I approach 0 from the right-hand side, and my graph goes down and down and down and down and down, it approaches negative infinity. The fact that I have 2 different values for my limits as I approach from the left side and the right side tells me this function is discontinuous. Now, down the road, we won't have the picture. We'll be working with our function. But the idea is, if we get different values for limits, that has to be discontinuous. As you approach from the left and the right, the graph is doing different things. That's kind of what we're trying to get across with this picture here. Let's look at the third one, letter C. Okay. I notice there's a discontinuity at 2. So if I were to write down as we approach 2 from the left, what do we notice about our function? It seems to be getting closer and closer to, let's call this 1. Okay, so our graph is getting closer and closer to that 1. But as I approach from the right, our function seems to be getting closer and closer to 2. What does that tell me? Well, again, it tells me different values. This is discontinuous. Okay, again, we can see in the picture it's obvious, but down the road we want to be able to prove, just looking at our limits, without a picture, that this is discontinuous, and I can because different left and right hand boundaries. And that's a jump discontinuity we'll talk about. Okay, last one. Remember back to higher functions, this has a hole in it, which we know is a break in your graph. Okay, if we look at the hole, which is at 0, and we approach it from the left, we get, we're getting closer and closer and closer to, it looks like 2, right? If we approach it from the right, that function, we get closer and closer and closer to 2. Well, based on this, our limit exists. The limit of the function gets closer and closer to 2, the closer and closer we get to 0. But we know by looking at the picture, this is just continuous. So there's this one situation we're going to have to worry about when we don't have a picture. Our picture tells us discontinuous. But if we didn't have a picture, we would assume that this function is continuous because we had our limit from the left and right equaling the same value. So holes are one of our special cases. The other ones are pretty obvious. They're different values. But with the holes, you get the situation where it looks like the limit exists when the graph is actually discontinuous. And we'll come back to that idea down the road a little bit. All right, you guys can try the next one. So you use my graph. Can you figure out some different values off this graph? So as we approach 1 from the left, we get closer and closer to 0. As we approach 1 from the right, we get closer and closer to 2. Question C is saying, what is the point at 1? Well, the point at 1 is actually right here. So our function value is 1. What would you say about the limit at 1? You would say it doesn't exist, because from the left and the right you have different values. Part D, as we approach 2. Well, from the left we approach 2, we get to here. From the right we approach, we get here. Either way, you get a limit of 3. And we can do that because from the left we have the same value, from the right we have the same value, which means that limit exists. Okay? You would not be able to, just to point out this, figure out that value. Because at 1, you have 2 different values, so this would not exist. Okay? But every other point, it does for that function. Okay, so I want you to use the equation now. No more pictures. Can we figure out if our limits exist? Okay, so we slowly want to take away that picture. How can we do this? Well, we need a left hand and a right hand limit. So I need to figure out, as I approach from the left for my function is just this thing, what kind of values do I get? So let's pick a number to the left of -1. Let's see what we get. So a nice number close to -1 would be -1.001. That's just really close. We'll plug that in. And we get approximately 2.006. And I'm thinking the closer I get to the 1, the closer this gets to 2. So I'm going to say it's approximately 2. If we do the same thing, but we approach -1 from the right, what's the number to the right of -1? It's -0.999. Let's see what happens there. So -0.999. Just plugging into our equation, we get approximately 1.994. And I bet the more 9s I add, the closer and closer this gets to 2. Okay, now it isn't 2 obviously, but I'm thinking the closer and closer I get to the -1 situation, the more and more it gets closer to this. So what can I say about that limit? I can say as I approach -1 from the left and the right for my function, it seems that I approach 2. So my guess would be that this function is continuous at -1. That's our whole idea about continuity, okay? Okay, give B a try, see if you can do the same ideas. You give it a try. So what happens as we approach 0 from the left for this function? So if I were to try, I don't know, -0.001, we would get 5 over -0.001 cubed. And what does that come out to? That's a really big number. It's -5 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, that's the left-hand limit. As we go to the right-hand side and approach it, so let's go just a little bit to the right. Let's try +0.001. What's going to happen there? Well, there I end up with +5 billion. So what does that tell me about this graph? Well, that tells me this graph, this limit at 0 does not exist. And if it doesn't exist, we know for sure, this graph is discontinuous. And where is it discontinuous? At x equals 0, which we kind of already should know, because if you remember something about asymptotes, whenever you get an x on the bottom, you get yourself a vertical asymptote, a break in the graph. But I proved it by using my idea of limits. And that's our idea in this unit is we're going to start formalizing our understanding of things as opposed to just remembering bigger on top, bigger on bottom, zeros at the bottom. We want to have a formal definition. Okay, last part. Can you sketch this function for me and then determine if the limit exists? We call these piecewise functions, if you recall. If we take the first part, x squared minus 1, but I only want the parts where x is less than or equal to 0. We might remember this as a parabola. We should be good at drawing parabolas. They have a vertex. The vertex is 0, -1. They have a step pattern. Our step pattern here is supposed to be 1, 3, 5. And because there's no a value, it really is just 1, 3, 5. So we can start at 0, -1. And be careful here now. We only want the parts where x is less than or equal to 0. So in other words, we only want, here's where 0 is, right? We only want the parts to the left of that. So over 1 up 1, over 1 up 3, and so on. There's my first part of the piecewise function. The second part is one of our parent functions from grade 11. And with these ones, we usually start with tables. The basic table was 0, 0, 1, and square root of 1 is 1. You could do 2, but then you get square root of 2, which is a big decimal. So we usually skipped to 4, because square root of 4 comes out to 2, and 9 was 3, and so on. We don't want to include 0. We want to get close to 0, but never actually hitting 0. So if you recall, that means you have a hole at 0, because we have just the greater than part. So we're going to draw it like a hole, an open circle, if you will. And then we have 1, 1, and 1, 2, 3, 4, and 2. We end up with this picture. So we got ourselves a piecewise function. The second part of the question asks, does the limit as x approaches 0 exist? Well, from our picture, we can see there is a jump discontinuity. So we know the limit does not exist. So as we approach 0 for this function, does not exist. And the reasoning we would give behind that, our formal definition would be since the limit of our function as we approach 0 from the left, what happens as we get from the left? We get a value of -1, right? This point right here. And as we approach it from the right, so the limit of our function as we approach from 0 from the right comes out to, well, that was where the open circle was, the hole, right? So since our left-hand limit and the right-hand limit do not agree with each other, that limit does not exist. Okay, and that's sort of an introduction to how we can start using limits to analyze functions. Are they continuous, discontinuous? What weird things go on here? And I really am going to ask you guys to formalize things, not just remember ideas of, oh, it's a axis of symmetry, sorry, the x on the bottom means a vertical asymptote. We want to have a more formal idea to this.